A pilot, to be skillful, must have more than an elementary knowledge of how to move the controls. He must have an adequate concept of the forces which act upon his plane, the way in which these forces may be advantageously used, and the limitations of his airplane. Now, to have complete mastery of his airplane, the pilot must understand why an airplane flies and how his application of the various controls affects its flight. Equipped with that understanding, he is able to fly within safe limits, to avoid dangerous practices, and to deal correctly with unexpected or unusual situations. Now, this recording, Theory of Flight, is a means by which you will be able to learn the truth behind powered flight. Enclosed with this album is a manual which is to be used as an integral part of this course. Do not listen to this record unless the book is in front of you. References will constantly be made to the numerous illustrations throughout the manual. The sound of a jet aircraft is heard. As we gaze skyward, we can't help but wonder what keeps those airplanes up there. Well, the reasons aren't very difficult to understand. Plate 1 shows the force that makes flight possible. That force is called lift. Lift is a force that is a result of atmospheric pressure acting upon the wings of an airplane. Before lift can be completely understood, a knowledge of the effects of an airflow is essential. Plate 2 shows a very special type of hollow tube. The ends of this chamber have larger openings compared to its narrow center section. This tube is called a Venturi tube. Plate 3 shows some air being blown through the left-hand opening of the chamber. As the air flows toward the center, it begins to travel through a smaller and smaller opening. Since large volumes of air are still entering the tube from the left, the air in the narrow center section is forced to speed up and make way. Whenever a stream of air travels through a narrow passageway, it is forced to pick up speed by the pressure of the large volume of air pushing onward toward the center of the tube. This fact is not only true of air, but also of water. Refer to Plate 4. It may have been a long time since you've gotten into a water fight with a garden hose. But remember when you were unable to reach your opponent because the hose wasn't long enough? Plate 5 shows a simple solution to this problem. All that was necessary was for you to put your thumb over the end of the hose. The water would then come out much faster and consequently would travel much farther. Result: your opponent got wet. Plate 6 shows why. Without realizing it, you were creating your own Venturi tube. Just like air, the water was forced to speed up due to the pressure of the larger volume of water approaching the nozzle. Your thumb was the cause of the restriction, which is essentially the narrow portion of a Venturi tube. Now, we're going to leave the Venturi tube alone for the time being, but remember this principle. The velocity of air will always increase when traveling through relatively small openings. In the back of the Theory of Flight manual, there's a slip of paper. Take it out and hold it close to your mouth, as shown on Plate 7. Now, very slowly and easily, start to blow across the top of the paper. Blow a little harder, and just a little harder yet. The paper lifted, didn't it? As air flows over an object, a semi-vacuum or suction is created. The faster the airflow, the more the suction. This is what caused the paper to rise. Air flowing over the paper caused a vacuum, and the paper lifted. Atomizers and flit guns work on this very same principle. Plate 8 shows an atomizer close-up. The bulb is squeezed, and air is forced to pass over the opening of the tube that leads to the liquid in the container below. Since the air is flowing over the end of the tube, what do you suppose will happen? A suction or low pressure area is formed, and the liquid is drawn up the tube and then is blown out the front. The liquid was drawn up the tube in the same manner that the paper was lifted when you blew across the top of it. Now let's summarize what we've learned so far. Plate 9. As air is forced into a restricted area, it increases in speed. Plate 10. When air flows over a surface, a vacuum or low pressure area is formed. The faster the air flows, the greater will be the suction created. Just remember, air speed reduces pressure when flowing over an object. In just a few moments, we're going to apply these two principles to an airplane. But first, let's learn a little about the wing of an airplane. After all, this is what keeps the ship up. Plate 11 shows a cross-sectional view of a typical wing. The front edge of the wing is called the leading edge. The rear edge of the wing is called the trailing edge. An imaginary line connecting the leading edge and the trailing edge is called a chord. The curved surface forming the top of the wing is called the camber. A wing is said to have a large degree of camber when the top of the wing has a large curve. Plate 12 shows two wings. One has a high degree of camber, and the other has barely any camber at all. Become familiar with the various parts of a wing. We'll make reference to them. Plate 13 shows our typical wing in flight. The arrows represent air flowing over and under the wing. The straight lines above the wing represent an undisturbed, smooth flow of air. Take a careful look at the air flowing directly over the top of the wing. The air flowing over the top of the wing is traveling through a constricted area, bounded below by the camber of the wing, and bounded above by the smooth layer of air. In other words, the air flowing directly above the wing is flowing through an area very similar to a venturi tube. And you know what happens in a venturi tube. The velocity of the air increases. Now you can see the purpose of having camber on a wing. The camber forms a semi-venturi tube. As the air speeds over the top of the wing, the results can be seen on plate 14. The increased airspeed over the wing creates a low-pressure area, and the wing is forced to lift. Blow across the piece of paper again. Watch it rise. The force causing the paper to lift and the force causing the wing to lift are one and the same. Air flowing over the curved surface increases in speed, and in doing so creates a vacuum, and the object rises. This is why an airplane is able to fly, any airplane, no matter how large or how small. The most important function of a wing is to create lift. Anything that's designed to create lift is called an airfoil. It should be obvious that a wing with a high degree of camber is capable of producing more lift than a wing with limited camber. A large camber will create a narrower venturi effect. Plate 15 shows the cross-sectional view of a high-lift wing and a low-lift wing. The high-lift wing is used on aircraft designed for carrying heavy loads. You can readily see that the bulky high-lift wing would have much more air resistance than the low-lift wing, and would not be able to go as fast. Fighter and pursuit-type aircraft employ the thin, low-lift wing in order to attain the high speeds they do. In observing a few of today's modern aircraft, it is easy to spot a wing designed for high lift or a wing designed for high speed. The camber of the wing tells the whole story. On the majority of aircraft, however, a compromise between high lift and high speed is made, and a medium camber is used. Lift is one of the four major forces acting on an aircraft in flight. Another force is shown on plate 16. Now, as you may have already guessed, gravity, or just the weight of the airplane, is the second force. After all, if the ship had no weight, it wouldn't need lift. Plate 17 shows a third major force, thrust, or the forward motion of the aircraft. Thrust is provided by the propeller or propellers on multi-engine aircraft. Plate 18 shows how the propeller pulls the airplane through the air. It pulls the airplane in the same manner that a boat would be pushed through water by its propeller. The power required to rotate the propeller is provided naturally by the engine. Although jet engines operate on a different principle than piston engines, the thrust produced is the same. It is still a propelling force. Both types of engines have one thing in common. Additional power must always be applied to gain additional thrust. Many people are under the impression that if you double the power of an airplane, you will double its speed. Well, this is not true. If it were, today's light aircraft would probably be cruising at speeds in excess of 500 miles per hour. Refer to plate 19, and we'll see why this is so. The main necessity for thrust is to counteract the fourth force acting upon an aircraft in flight, and that force is air resistance, or drag. Air resistance, or drag, tends to resist the movement of an object through the air. This is illustrated on plate 20. The faster we go, the more drag we encounter. If you're traveling 30 miles per hour in an automobile and put your hand out the window, you'll feel the air resisting your hand. Double the speed of the car to 60 miles per hour, and you'll notice the air pressure on your hand will quadruple. Now, if you do the same thing and double the speed of an airplane from 100 miles per hour to 200 miles per hour, the air resistance will again quadruple, as shown on plate 21. In other words, even though you only double the speed of an object, its drag will be increased fourfold. In order to counteract this added air resistance, the thrust or horsepower of the engine must not only be doubled, but actually must be more than quadrupled. As the drag increases, the power must be increased proportionately. Now, let's assume that you did install a very large engine in your plane so as to double its speed. The larger engine, along with the added fuel it requires, will, of course, burden the airplane with additional weight. If you increase the weight of an airplane, you will naturally need more lift. And the only way to increase the lift of an airplane is either to enlarge the wing or increase its camber. And this would create even more drag, and you'll need more power yet. Plate 22 shows the vicious cycle that plagues every airplane designer. You can't have everything in an airplane. You must sacrifice speed to get high lift, or vice versa. Well, you should now have a firm understanding of lift, drag, thrust, and gravity. These four forces act the same on a J-3 Cub as they do on a Boeing 707. You now know why an airplane flies. If you don't thoroughly understand this first lesson, do not proceed. Repeat the lesson over and over until you are sure you have learned it well. When you think you're ready, take the examination for Lesson 1 in the back of your manual. You are then ready for Lesson 2.